Hello, this is the pre-lecture video for Chapter 2, Part 1. Today we'll be talking about atomic theory, some atomic particle discoveries, modern atomic theory, and the periodic table. So the atomic theory of matter began to develop in the 1800s and 1900s. John Dalton kind of led the way in the early 1800s. He began with his work on proposing the law of constant composition. What this means is that a particular compound would be comprised of molecules of the same type. So this kind of began this notion that a substance would be characteristic of a particular particle, and then those particles would have a constant composition. And so then also from this work led to the law of conservation of mass, that you could convert one substance to another just by rearranging the arrangement, if you will, of what later became known as atoms. But then in the process, you had to conserve mass. So you could not create or destroy mass in this process. And also came from this is the law of multiple proportions, that if you're going to make a compound, that it would have a ratio of the elements that's making up the compound. So maybe you have one carbon to every two oxygens in a particular type of compound, and that ratio would be a constant. Dalton made a few postulates about atomic theory. One is that elements were said to be composed of extremely small particles called atoms. And so then you can have different types of atoms, such as oxygen atoms and nitrogen atoms, that are different from each other. All atoms of a given element are identical to each other, but the atoms of one element are different from atoms of the other elements. So you have oxygen atoms, all the atoms of oxygen would be the same, according to Dalton, then all the atoms of nitrogen would be the same, again, according to Dalton. Now, we're going to see later that there are different types of isotopes that are possible. So maybe we can look at oxygen after Dalton in the 1800s and learn that, oh, there actually are different isotopes which make some of the atoms of oxygen slightly different from each other. So we'll see that postulate 2 isn't exactly true, but this is one of his postulates well before anything was known about neutrons and isotopes. Atoms of one element cannot be changed into atoms of a different element by chemical reactions. So you cannot just convert oxygen to nitrogen if you need more nitrogen. And so there's just no chemical way to be able to do this. Now, there are some nuclear decay pathways where elements are interconverting to and from each other, but these are relatively slow reactions that take place on the lifetime of our universe for some of these reactions, and they're not going to be like practical reactions that we carry out in the lab for the sake of needing some new type of element. And so then compounds are formed when atoms of more than one element combine and they give you a new compound, such as taking N and O, bringing them together to form the compound NO. So we learned in Chapter 1 that a compound contains at least two different elements. So we see here kind of the multiple proportions in this compound would have one N to one O for every one of those particular molecules of that compound. So the key here is that you get the ratio of the elements coming together to form a compound. Now maybe you could take N with two O's and form a new compound like N2O, or NO2, or maybe take two N's and an O and form N2O. So you can form different types of compounds, or you can imagine forming different types of compounds through the different ratio of elements coming together. So let's begin our discussion of how the subatomic particles within an atom came to be known. The electron was discovered, or began to be discovered through a set of experiments beginning with a cathode ray tube experiment. You can make a cathode ray by taking a gas and then subjecting it to a high voltage of electricity. And then you could see a steady stream of a particle that's generated, and then you could bend that particle's trajectory using an electric field. And so this particle was then further investigated. Let's go to the next slide. So the particle is further investigated. This is really the cathode ray tube where you have a fluorescent screen that would light up if this particle is hitting your screen. You could have a magnetic and electric field that you could apply and bend the trajectory of the particle in such a way that the negative particle is going towards the positive direction of your electric field. So this definitely was establishing that the electron was negatively charged. It was our negatively charged particle. Thomson measured the charge to mass ratio. You don't need to know this number or memorize it, but it turned out to be 1.76 times 10 to the 8 coulombs per gram. Now, this in and of itself didn't necessarily suggest that the particle was subatomic for sure, but they believed it to be a subatomic particle, something smaller than the smallest known atom. Millikan then provided the experiment that definitively proved and was able to determine the mass and the charge of this subatomic particle. So what Millikan did was he did something similar. Now this is just almost unnecessary detail. He took oil, atomized it, just so you could get individual atoms flowing through and downward. And it's kind of important that you imagine these particles flowing downward just basically from gravity acting upon these atoms. And so then you could take an X-ray, a high energy source, and then use that energy to create these subatomic particles in a similar way to the way J.J. Thomson was doing this in our previous experiment. And so then the thing that changes is you could have a negative particle form on these atoms, and then you have a positive direction of your electric field that you can adjust and sort of see that you can bend those particles back upward. And since you're comparing the particles' fall of gravity versus their bending or how fast they're flowing back upward towards the positive direction of the electric field, what this allowed Millikan to determine is that there was like a whole number multiple of the particles, the subatomic particles that each of these atoms contain. So you could almost see what we now would say would be, well, you'd have a particle with 1 or 2 or 3 electrons attached to it. And so then what Millikan then was able to do was establish the actual charge and the mass of the electron along with J.J. Thomson's previous experiment. And so this allowed the definitive determination that the electron was subatomic, it was lighter than the smallest known element, and then that it was negatively charged, and allowed the establishment of that actual charge. So another important experiment on the way of atomic discovery was the radioactivity experiments by Ernest Rutherford, also by Marie Curie. Part of this discovery was by taking a radioactive substance. You could see 3 particles coming off this substance. One was able to be bended upwards towards the positive direction of the electric field. This is our negative particle. This is our electron. So the beta ray is our electron. The red beam is the one going downward. That's our alpha ray. This turns out to be a helium nucleus. It's our neutron and our proton within a nucleus. So it's the positive particle that we'll later see is within the nucleus of the atom. But scientists at that point didn't really know much about the nuclear model of the atom. Also, there was a high energy photon that was observed, and it went straight through the electric field. It wasn't bended upward or downwards because it doesn't have a charge associated with it. And it also turns out not to have a mass associated with it either. So radioactive material can give off beta rays, electrons, alpha rays, helium nuclei, or high energy packets of energy, which are gamma rays. So if we now have our atom is comprised of relatively light electrons, relatively more massive particles bringing about the positive charge, the next question might be, where are these particles situated in the atom relative to each other? J.J. Thomson proposed that the positive protons would be interdispersed among the negative electrons. But this may not make much sense, as the electrons are going to be moving at a much faster velocity due to their small size compared to the more massive protons. To test the model of the atom and to try to learn a little bit more about the structure of the atom, Ernest Rutherford shot alpha particles, if you recall those were the helium nuclei, at a thin sheet of gold foil, and observed some scattering taking place. Now what you might expect if you had this plum pudding model is you'd really just have empty space for the most part in the atom. So if you shot a beam of particles through a thin sheet of gold atoms, you'd mostly just have empty space, and you'd probably expect most of the particles to go straight through the foil, or maybe some be deflected just a small amount if they happen to come across a relatively small proton. But now if you instead had all of the positive particles centered around a more compact nucleus, you then have a larger center which then could explain the observation that Rutherford saw of some large angle scattering. So you see some scattering, even some backscattering, and so the suggestion for these wide angle scatterings would be that you have relatively large compared to one single proton. So a relatively large nucleus compared to a proton, but compared to the size of the atom, a relatively compact nucleus containing the charge. And if the alpha particle strikes sort of dead on or near that nucleus, then it's deflected at a large angle. Otherwise, the particles pass straight through. So it was this large angle deflection that really supported the nuclear model of the atom as opposed to J.J. Thomson's plum pudding model. So Rutherford postulated a very small, dense, positive center around which the electrons are surrounding the nucleus. So we'll get into what the electrons are doing in chapter 6 around this atom. So for now, we'll just have it as a sphere. But the electrons, we're going to see they're in orbitals. You probably know that already. But the electrons reside or can be described as being in orbitals surrounding the nucleus. Most of the atom is just empty space, it turns out. And most of the mass is that little center in the nucleus of the atom. Atoms are very small, about 1 to 5 angstrom in size. They're so small, they invented a scale. So 1 angstrom is 10 to the minus 10 meters. We could have used nanometers or picometers, but angstrom is a bit more convenient. So our total diameter of an atom is about 1 to 5 angstroms, depending on the specific atom. And so then we'll get into nuclear size trends in chapter 7. Other subatomic particles are found in the nucleus. So we have our protons and our neutrons in the nucleus. The protons we'll see define the atom. That'll be the key, the positive particles that there are, the number of them define the atom, and then the electrons will define the charge. So we'll see that the electrons can be easily added or removed from an atom. The protons, we're not easily changing the number of protons by simple chemical reaction means. So now let's get into the subatomic particles. So protons have a +1 charge, and electrons have a -1 charge. So meaning that they are equal and opposite, equal in magnitude, opposite in their charge. And so neutrons are exactly neutral. So protons and neutrons have essentially the same mass. In the atomic mass unit scale, and we'll get into that scale a little bit more in the next chapter, but 1.0073 AMU for the proton, just a little bit more massive for the neutron. The electron has a much, much smaller mass, 5.486 times 10 to the minus 4 AMU. Now the actual charge here is about 1.6 times 10 to the minus 19 coulombs. So minus 1.6, and then of course plus 1.6 times 10 to the minus 19 coulombs in terms of their actual charge. So let's go over some nomenclature for how we can give symbols for our different elements. Our different elements, of course, each have their own abbreviation, and then the element themselves are defined, their atom type is defined by the number of protons within the nucleus of that atom. What makes carbon-carbon is having 6 protons in its nucleus. What makes nitrogen-nitrogen would be having 7 protons in its nucleus. And so then our mass number is the number of protons plus the number of neutrons. So 6 plus 6, so a number of neutrons in carbon in this nucleus here would also be equal to 6. That's not true. It's not true for all atoms that we'll see that they have an equal number of protons and neutrons within their nuclei. That's just true for this particular atom of carbon and for many or some of the smaller elements on the periodic table. So we see elements are represented by its 1 or 2 letter symbol. And so carbon, C, 6 protons in its nucleus. And then if the charge on the atom is neutral, then it has to have exactly the same number of protons and electrons. So this atom of carbon would also have 6 electrons to have a neutral charge. And then we'll start to see you can have a minus or a negative charge or a positive plus charge if you have electrons added or removed from that atom. So we can add to or remove the electrons from an atom relatively easily. We're not changing the proton or the neutron count by simple chemical means. So it's possible for certain elements, and really this ends up being the case for most elements, that they exist as more than one isotope. So isotopes are atoms with the same element but with different masses. We get different masses for these atoms when they have different numbers of neutrons within their nuclei. So for example, carbon, we have carbon 11 where we have 5 neutrons, carbon 12 where we have 6 neutrons in the nucleus, carbon 13, 7 neutrons, carbon 14, 8 neutrons. We can also use a different system to write this. We could call this element here, for example, carbon followed by the mass number 14. So two different ways we can go C14 with the superscript or write out carbon-14 for a slightly different nomenclature system. Now the thing that makes these isotopes different are the neutrons. Same number of protons, same electrons within these atoms, just a different number of neutrons. So let's talk about this atomic mass unit scale. So you can imagine atoms have a really small mass. The heaviest known atoms have a mass of about 4 times 10 to the minus 22 grams. It's really small. So a mass scale on the atomic level is used where the AMU is the base scale. So 1 AMU is equal to 1.66054 times 10 to the minus 24 grams. Now remember how earlier, in one of the earlier videos on conversion, so we were talking about like the nanometer is, there's 10 to the 9 nanometers in a meter, and there's 10 to the minus 9 meters in 1 nanometer. So you can define your conversion factor both ways. Well, what's 1 gram equal to? So how many AMU are in 1 gram? Because we get an interesting number here. So if we divide both sides by 1.66054 times 10 to the minus 24, we get that answer. If we do that arithmetic, that works out to be 6.02214 times 10 to the 23 AMU. Okay, now of course there's a lot of AMU in 1 gram, as we can see, but it's Avogadro's number. It's a number we've probably all seen before. So that works out to be Avogadro's number of AMU in 1 gram. Now it turns out not to be an accident. Like this isn't some voodoo trick that I've just done. What this arises from is the fact that we define our AMU scale very precisely to be the mass, or we very precisely define 12 AMU to be the mass of 1 carbon-12 atom. And then you very precisely can go determine the mass of this atom, and that it's 12 times that number of grams that you see listed above. So it's 12 times the 1.66 times 10 to the minus 24 number. So you just then very precisely go figure out the number of grams of this atom, set that equal to 12 AMU. We talk about that a little bit more in the next chapter, in chapter 3, where we get the definition of the mole to equal 6.02214 times 10 to the 24 things comprising a mole. But it's a very clever choice to define the mole to be precisely the number of AMU in a gram, so that you get this idea that if you know a carbon atom, for example, has a mass of 12 AMU, that its mass would also then be 12 grams per mole. So again, we'll talk about the AMU and grams per mole scale more in the next chapter, but I just kind of wanted to give a little bit of a foreshadowing of where the AMU and the gram scale, how they link together. So let's talk about atomic weight, and let's think about carbon in this example. Because carbon exists predominantly as 2 isotopes, carbon-12 and carbon-13, and to a very small extent, carbon-14. And so our abundance is about 98.93% carbon-12, about 1.07% as carbon-13, and less than about 10 to the 10%, or 10 to the minus 10% is carbon-14. So a very small fraction of carbon atoms is carbon-14. Now that's still enough for that to be useful for things like carbon dating. That's a topic you'll see in chapter 21 down the road. Now the thing that we might wonder is, well, what's the average mass of carbon? If you encountered carbon in nature, a sample of, say, graphite, what would the average mass of the atoms within that sample be? Well, the other thing you would need to know is, well, what's the mass of each of these isotopes? The mass of carbon-12 is exactly 12 AMU. This is an exact definition in the AMU system. So it's like 12.000000, etc. And then the carbon-13 mass is 13 0.00335. And the mass of carbon-14 is 14 point something. So for the sake of this example, we're not going to worry about the mass of carbon-14. So now, if we want to know and define the atomic weight of carbon, what we're going to want to do is take the weighted average of all of its natural occurring isotopes. And so the way we would do that would be to take the fraction that's carbon-12, so that's 0.9893 times 12 AMU, and add to that the 0.0107, the fraction that it's carbon-13, and then multiply that by the 13.00335 AMU. And if we work that out, that ends up giving us our mass. And if we just round this down, we'll talk sig figs, or we could talk sig figs later. It works out to be about 12.01 AMU. So the mass should be just a little bit higher than the mass of carbon-12, since the other isotope's a little bit heavier than carbon-12. But not much higher because it's very infrequently our carbon atoms carbon-13, only about 1% of the time. Okay, and so most of our carbon's carbon-12, a little bit's carbon-13, so few of it's carbon-14, we don't need to even factor it into this particular calculation. So now if you look at the periodic table, you see 12.0107, or depending on the precision level of the mass listed for carbon, you might see a few more digits included. That's just from doing a little bit more of a refined calculation. So now you can imagine doing this for all the elements. That's what we want to know and list on the periodic table is the average atomic weight, the average mass of all of the natural occurring isotopes for that particular element is what you find on periodic tables. So the way atomic weights and the abundances and the masses are determined are using an experiment called an instrument called a mass spectrometer. The way a mass spectrometer works is you would put a charge on these atoms, and then depending on the mass to charge ratio, the atoms would bend to a different extent through a magnetic field. And so then you could very sophisticatedly, using this technique, determine the abundance and then the specific mass of these isotopes, and from that information determine the average atomic weight. And so you see here the two common isotopes of chlorine are chlorine-35, chlorine-37. The atomic number of chlorine is 17. So we've got 17 protons in the nuclei here. So 17 subtracted from 35 gives us 18 neutrons for the lighter isotope and then 20 neutrons for the heavier isotope. And so then if you could determine these masses and abundances very accurately, you can then come up with the average atomic weight for the element of chlorine. So we see our periodic table listed here. So our elements are grouped in order of increasing atomic number and then grouped by elements of similar properties. So probably the most notable group of elements are the noble gases because they're all gases. It's the only group of elements that are all gases. And then another notable group are the alkali metals. They're all metals that are easily oxidized. They easily lose an electron. Other metals aren't as easily oxidized as these elements here. And so then they also have like similar melting points and things like that. The alkalines are the next group of elements, and we have the transition metals. Now these elements all somewhat behave similarly. They're not exactly the same, but they have similar properties. Our halogens are the group right before the noble gases. They all easily gain an electron and form negative ions really easily, kind of like the counterpart to the alkali and alkaline metals, which are easily losing electrons relatively easily. So we see our elements are grouped in order of elements in the vertical columns that have similar properties, and then in rows by increasing atomic number. I do want to point out the elements that you should know the symbol to name or name to symbol. So if I say the name, you should know the symbol, and vice versa. If I use a symbol, you should know the name. Those would be your alkali and alkaline metals. This would be our first two rows over here. All of the noble gases through xenon, all of the halogens, and then most of the first row of our transition metal series, are worth knowing the name to symbol, symbol to name. And then lastly, I would recommend knowing gold. That's not gold, that's silver. Silver, gold, mercury, and then lead. So these are some of the most common elements, and also tin, Sn. And so you don't have to memorize their positions on the periodic table or any of the numbers associated with them. Just name to symbol, symbol to name. And finally, our last slide, we see here a summary of some of the names of the groups in the periodic table. Alkalis, lithium through cesium and francium. I usually just say through cesium because francium is radioactive, but that's neither here nor there. Alkali metals, beryllium, magnesium, calcium, strontium, barium, radium. Our chalcogens, that's the oxygen group of elements. Halogens, the fluorine group of elements. And the noble gases, the helium group. So I would know these 5 groups by name. So if we say the chalcogens or the halogens, I would expect you to know the family of elements that we're referring to. So that really summarizes our introduction to the first half of Chapter 2. Thank you for your attention.